For our topic, we chose to take a deeper look into the propulsion of rockets. The propulsion of a rocket is interesting because the initial weight of a rocket is mostly comprised of its fuel. As the rocket uses this fuel, it becomes lighter, and therefore a constant force upon the rocket will create an increasing acceleration. Now, if we want to find the amount of fuel it would take to complete a certain maneuver, a specified delta V, we have to derive an equation that takes into account this effect of the decreasing mass of the rocket. First things first, we want to figure out the forces acting upon a rocket as it flies. Or in other words, we wanted to know what makes a rocket go whoosh through the sky. Of course, the first thing we did was watch videos of rockets so we could see the forces acting upon them. As you can see in this video, the reason the rocket lifts is the fact that it's launching gases out of the nozzle very fast. These gases are accelerated and shot on the bottom of the rocket, making a force equal to the mass flow rate, m dot, times the velocity of the propellant, v sub e. The mass flow rate is the amount of fuel that passes out of the nozzle of the rocket per second. In accordance to Newton's third law, the rocket experiences an equal and opposite force to these expelled gases. With this information, we can state that the force of the rocket is equal to the negative force of the thrust, and since the force of the thrust is downward, this results in the force of the rocket being positive, or upwards. Now, according to Newton's second law, force is equal to mass times acceleration. If we rearrange this equation, it can be seen that the acceleration of the rocket will be equal to the force it is experiencing divided by its mass. Now we know the force the rocket is experiencing is equal to the force of the thrust, so we can substitute in m dot times v sub e for F. The mass of the rocket can be represented with the function m sub r equals m naught minus m dot times t, where m naught is the mass of the rocket at t equals 0, and m dot times t is the amount of fuel that has been expelled from the rocket. For this derivation, we're going to ignore the force of gravity and drag, so these are all the forces needed to calculate the acceleration of the rocket. For our equation, we want to find the delta V of the rocket, so we integrate the rocket's acceleration with the limits time equals 0 and the final time t sub f. Now to simplify this to a usable equation, we have to do some calculus. We can take m dot and v sub e out of the integral as their constants. Then, we can do a u substitution for m naught minus m dot times t and pull out the 1 over m dot that was substituted in with du. Now, we just take the integral of negative 1 over u, which is the negative natural log of the absolute value of u, and then plug back in m naught minus m dot times t for u. At this point, we're going to go ahead and substitute in m naught minus me all over m dot for the limit t sub f. This equation is basically stating that the initial mass of the rocket minus the final mass divided by the mass flow rate is equal to the time that it takes for the rocket to use all its fuel. An example of this would be a rocket that's 20 pounds when full, 10 pounds when empty, and has a burn rate of 2 pounds per second, which would have a burn time, t sub f, of 5 seconds. We do this so that our function is in terms of the mass of the rocket and its fuel instead of time. Now, after evaluating on the limits, the equation can be simplified to this, and then this. Now, if we want to include the force of gravity, we just subtract g naught multiplied by delta t, as gravity is constantly accelerating the rocket downward for the duration of the burn. This is the ideal rocket equation, also known as the Tsiolkovsky rocket equation. Now that we have this equation, what can we do with it? Well, we can use it to find what change in velocity will occur with a certain initial mass and final mass, or if we rearrange the equation, it can be used to determine how much fuel is necessary to complete a specific maneuver. Let's say we have a rocket floating around in space. This means we can ignore gravity. It's moving with a velocity of 5 meters per second, and the empty mass of the rocket is 30,000 kilograms. If a rocket has 200 kilograms of fuel and an exhaust velocity of 31,000 meters per second, what is the velocity of the rocket after a complete burn? For this problem, we can just plug in the given values, and we get that the delta V is about 201 meters per second, giving us a resultant velocity of 206 meters per second.
Let's try another example, this time one from real life. During the Apollo missions to the moon, the third stage of the rocket, the S-4B had to provide a sufficient delta V to get the spacecraft out of Earth's orbit and send it to the moon, a process called translunar injection. Let's figure out how much fuel was required to perform translunar injection. We know that the required delta V was 10,200 feet per second. The exhaust velocity of the stage's J2 engine was 15,740 feet per second. And the final empty mass of the spacecraft was 2,973 slugs. Now let's solve the rocket equation for final mass. Now all we have to do is shove our numbers in and find the required initial mass and subtract the empty mass of the spacecraft to get the amount of fuel we need left over. And we find that the required amount of fuel is 2,700 slugs, or 87,300 pounds.
In this video, we learned about the forces acting upon a rocket as it flies, the derivation of the ideal rocket equation, and a few applications of this equation.